Can you hear me?
Yeah.
Perfect. Okay, so hi, my name is Roman, and I'm going to be introducing Haskell, talk to you a little bit about the differences between Haskell and Erlang, and then go dive into Cloud Haskell, which is a library that really smart people implemented to replicate as much of Erlang as they could. So, my goal here is supposedly to make you switch to Haskell, which I think, let's see how we go. So I wanted to start with a small table difference between Haskell and Erlang and
Feedback.
Is there more feedback?
Yeah, a little bit.
Okay. Better? No.
No. Turn it down.
Down. Let me see.
The volume down.
The volume. Better?
Yes. Yeah.
Okay. So I was in order to do this talk, I was investigating a lot about what people in the Erlang community think about Haskell, and I found this interesting conversation between the creator of Erlang and Simon Marlowe about what things they saw about the two languages and what they share and what they not. And the first thing that came out was the background of the language, where Erlang was always hands-dirty, solving enterprise solutions from the get-go. Well, Haskell was basically just an idea that you could do everything with lazy evaluation, and how they sold that to people and create a language from that perspective. These two languages come around from time to time. Like you have people like John Hughes that comes from Haskell and then goes to Erlang, people from Erlang to Haskell. Like the people that implement the cloud Haskell, they have their roots in Erlang. So there's a lot of affinity between these two languages, which is quite cool, given that they come from completely different backgrounds. And one thing that I was wondering was, in the threading model, the concurrency model, I was asking Omar yesterday or 2 days ago, what was the way to solve every problem regarding concurrency in Erlang? And he told me, well, you just have actors, right? And I was like, that's interesting. Because sometimes actors are great, don't get me wrong. It's just that sometimes problems become easier if you use a different abstraction for concurrency. I'm pretty sure you're able to do everything in the actor model fashion, but it's definitely going to be easier if you start thinking out of the box a little bit and approach into different things. And that different approaches, and that's the way Haskell does it in a way, where in Haskell you have threads, share memory, a lot of applications break because of that, of course. But you have a way to do software transactional memory. Who's familiar with that term here? Just raise your hand. Fair amount. For the people that is not familiarized with that, it's basically having some sort of database transactions through variables and being able to manage concurrency through that. So if two threads are changing a variable, then the transaction is going to repeat, and that way they go. That avoids surprisingly a lot of deadlocks on your code, because locks sometimes it's really difficult. It's really tricky to do it right because you have to unlock and lock on a specific order in order to avoid deadlocks. But with software transactional memory, it's really straightforward. And they have also a differentiation between what concurrency is in terms of control of applications and what the concurrency you will have for parallel applications. And they actually abstract the two so that you don't shoot yourself in the foot while you're trying to do a concurrent solution for parallelism specifically. That's something I found pretty clever. All the difference that bites a lot of Haskellers in the ass is lazy evaluation. Anyone that is not familiar with lazy evaluation, or what does it mean? Who knows what lazy evaluation means here? Everyone, perfect. And they try to sell Haskell as this language that works, that proves the lazy evaluation is the way to go. And I'm gonna have a really personal opinion here. That is that I think Haskell started to become way useful than it was before when they started to realize that I/O and laziness were like just the stupidest idea ever. But like lazy has interesting consequences. You can do way more elegant algorithms when you have laziness there, but you don't need it all the time. And most of the times, like the vanilla Haskell developer won't use laziness for anything fancy. So I think Erlang has a win there. Don't get me started with hot code reloading. Basically, if you want to do hot code reloading in any other language that is not Erlang, you're basically fucked. So there's a lot of things to envy to Erlang. And specifically the concurrency model, even though Haskell has all these different approaches, there was still concerns because like reliability is not as present in Haskell as it is in Erlang. And like the philosophy of concurrency with Haskell is better said by Simon Marlowe in his book, where he says, if we want to make programming concurrent and parallel software easier, that would replace that easier with less complicated or less difficult, because it's still difficult. We need to embrace the idea that different problems require different tools. So, in Haskell, we aim to provide the right tool for the right job, for as many jobs as possible. I think that's a really good philosophy to stand by, and I support that all the way. So, given this philosophy and seeing how Erlang works, you start to get the envy bug immediately. You're like Erlang is freaking awesome. Like OTP, like when you start learning about supervisors and Gen servers and all this stuff, like Fred said, it's like, I want that, but I don't want to give up my Haskell stuff as well. So a lot of smart people in Haskell say, well, let's just build an actor system then. And when we are in doubt, just rip off everything you see from Erlang and OTP, and that's the way to do it. Okay, perfect, let's just go to that. Okay, so why the focus on staying in Haskell and not going to Erlang if you want OTP, things like? There's a lot of things that Haskell brings to the table, and I miss a Zhao Ming face there as well. Like, we have types, you don't, duh. You know, that's the first thing. You're like, yeah, you want types to make your software safer. Of course, you don't need it to make software a real thing. Like, you haven't needed it yet, but like, types are the kind of things that make you dumber in a good way. Like, you start to rely less on yourself for avoiding stupid mistakes. And every time I don't program in Haskell, I'm afraid, sincerely afraid, because the compiler helps me a lot. And I really miss that when I don't have it. In the same lines of reasonability of software, purity in Haskell helps along the way. You are able to know for sure certain pieces of code or your system are not gonna be the ones, the culprit code on your failures, and that's amazingly well. You know, that's amazing. That's amazing. You can also inject like the purity on side effects, and that's something that is really nice too. Again, in case you have a problem where actors are going to become something of an annoyance, you have another concurrency strategies where you can sit on, and that's something I really like. And lastly, basically you have mods everywhere. You want that. Who here know what a mod is? Just wondering. That's a few number. That's a few amount of people. That's nice. Like so mods, what give you is a way to compose software in a way that is really difficult with other abstractions. Like, for example, the software transactional memory features you have. You can create specific transactions, and thanks to the concept of monads, you can compose them and make bigger transactions by just composing the smaller ones. The same way with parsers. You have a parser that just parses this little small thing, and you want to use that to parse a bigger thing, so then you compose it through monads or applicative functors, if you know what that is. Yeah, it's a lot of terminology there, and it's kind of unfair, I cannot explain it all, but I have someone here putting numbers, so. So how a distributed process works on, from Birdseye view. This will be really familiar to you. You have a bunch of nodes. Nodes can be on the same machine, or it could be different machines. You have processes in those nodes, and they communicate through messages. Simple. They don't share any state whatsoever. They shouldn't, unless like you can run like all the actor system on with a memory transport. Like all this transportation is done in memory, like the message sending and stuff. And that I think defeats the point, the purpose a little bit, because you have shared memory, but sitting on top of the abstraction of actors. But that's a good way to start. So you have ways to send messages. You can send untyped messages the same way Clojure will do it in Erlang. But at the same time, you have this API where you can send channels that have one specific type, and you're gonna go you're gonna divert from that. And that's pretty handy for several use cases. I won't use it all the time, but. And lastly, you can mix concurrency strategies. Say you have an actor that is implemented in Haskell already that uses a particular concurrency model. You can just have that as an actor running and supervise it with actors, and that's just amazing. Being able to use those abstractions already there in Haskell, which are pretty powerful, and put a TOTP layer on top of that. That's what everyone wants. So, what's some differences between distributed process and Erlang? Like, given that Haskell is a type language and you need to define custom types for everything you're sending around, you need to implement this serializable interface in order to send stuff through the wire. I'm not 100% sure, but I think in Erlang you don't need to worry about that at all. You just create from Erlang constructs and that's it. In Haskell, given that is the nature of this implementation is that it's a library that sits on top of Haskell. It's not like embedded on the runtime system. You can choose which transport you want. You want TCP, you want UDP, you want SSH. You have many different options that you can choose from. And yeah, as I said before, you have a way to do type messages, type channels, so you can send messages of a specific type and make things more reliable that way. And the oh crap limitation that this thing has is that you have to run the same executable on all your machines for this to work. And this has to do basically because of serialization. Like, given that you don't have a VM for running systems, like Haskell is running on the metal. And if for some reason implementation of serialization is different between platforms, then systems are not going to work.
I just wanted to point out, I have a suspicion that that's not 100% true, the last point. Because you need it if you're sending a closure of a function to a remote node. But I suspect if you're not doing that, you could probably cheat and have different binaries. Yeah,
but I guess they try to, like, the branding of this, and it's a branding I hate, it's just called Cloud Haskell. It was the possibility of having a cluster of machines and being able to send procs to it so that you can start different things, right? So, yeah, one question there.
Could you just clarify in your slide where you had processes in Cloud Haskell, what are those? Like in Erlang, in the VM, we know that when we say process, we mean this lightweight thing within the VM. Are those OS processes or things within a Haskell instance or whatever?
They are basically Haskell threads on rest, with address. Like Haskell threads are like the running on the runtime system of the Haskell executable, and they're like really cheap. Like there's
so in that sense similar to the Erlang VM where they're lightweight, not OS processes.
Yeah, they're like super lightweight, like
even lighter.
Even lighter, I would say. Well, that's unfair to say because Erlang provides so much more, right? But like on the thread level, but yeah, like it's really light. You can do millions of those, and you don't have to worry about that.
So these messages, then there's something like a language-specific sort of serialization protocol that's
I'm gonna go.
specific to an executable.
No, you basically have this interface that you implement.
Sure.
And like the way that interface is implemented on each of the platforms may change. That's the thing. Like the way the serialization algorithm works, which like the algorithms that you pass your serialized types to can change the serialization in a way or another. That's why it becomes a limitation on how you parse stuff. Like when you share things between machines are not the same acceptable.
Okay. I sense you're not comfortable with that.
Yeah, I don't like that at all.
How do you deal with rolling out new versions of a system where you will have part of the nodes with a version of the code and part of the other nodes with a different version of the code?
Yeah, you're basically screwed. And that's the bit that is like, oh crap, yeah. No,
So you need two clusters and just swap the needle between both of them.
yeah, basically. Okay. So yeah, target limitations. So node serialization. Imagine we're having this record here, ping pong, and we want to make it be able to send it over the wire to different actors. You will first have to derive this thing called typeable, which allows you to have some sort of type information on runtime. And can you hear me? Secondly, you have to implement the binary class type that allows you to serialize and deserialize. Like, if you're really picky about how you want a serialization, you are going to do this. You're going to do the instance yourself, and you're going to start doing bytes mapping to constructors and all that. But a nicer way to do it is using the generics API from the classical Haskell compiler, where you basically extend from a magic voodoo dark magic type class that's called generic. And after you do that, you can do instance binary ping, and it will definitely work out of the box. So that's pretty cool.
You're just taking a shortcut here, right? Because I think you could find your own message protocol. You could use Haskell just fine. Because we use your own custom message protocol, and you did this conversion of objects into this message protocol back yourself, right? It's not a limitation of Haskell. It's just you're doing something that's great.
Yeah, like the limitation. You mean the limitation of the same executables?
Yes.
Like
There's more to it.
like the thing is that limitation is there because you need to serialize functions, and when you start to serialize functions, things become pretty tricky. And the best solution they found is that at this point. I'm pretty sure they're going to find something better at some point in the future. Who knows? So, in order to start the actor system on Haskell, you need to use the process model. So you have one specific context where you can run your actors, and you're going to use like vanilla IO. In order to create this process context, you need to create a transport. And once you create a transport, you create a node where you pass transport in, so the node knows how to communicate to other nodes. And after you have that node, you can do a run process there, and you have the context where all the actor systems spread, and you can start doing sweet things with actors. In this specific example, we're using TCP as a transport, but you can use, again, SSH. Well, SSH is not implemented. The only two implementations there are right now is TCP and in-memory.
And zero Q.
And, is there one in review?
Yeah, third party one, yeah.
Oh, that's nice.
And Azure. Azure as well.
As what?
Azure?
Azure, yeah, right. The Microsoft people behind this, of course. So in this particular example, we are creating a transport, creating a node, and then running a node, a process, in that node. So spawning new actors. You have two ways to spawn actors. You can either spawn them in a way that you know they're going to be remote, like you know you're going to spawn on a different machine, or you can spawn on the local node. And you have two functions for that: spawn local and the spawn. And the spawn needs the node ID that you want to send the function to. There's also this this $NK static closure. Don't pay too much attention to that because I'm going to explain it later. But yeah, that's the way you create new actors from the current node. So at this point, you're running on the process model and you have access to all this API. If you're not running the process model, this won't compile. So with that type, to ensure that everything is set up in order to do what you have to do. Of course, you have the communication primitives, but they are a little bit like more specialized. Like you need to implement a serializable type class in order to send stuff. In order to receive stuff as well, you need the serializable, like the spec needs it. And in order to be able to receive any kinds of messages of any type, you need to use this match function, where you specify a function that receives the message on whatever type it is. It must, as long as it's serializable, will compile, and then returns a value b that is whatever this function A process to be returned. And then you use that in two functions, receive wait and receive timeout. This will be the equivalent to expect in Erlang. I will show a tidbit of code that shows how you do in Erlang, how you do in Cloud Haskell.
Very quick question for clarification. You're using serializable there, but on the previous slide you had typeable and binary. Can you explain how you get from binary to serializable?
Yes, thank you for the question. The way it works is that a serializable instance is whoever implements both typeable and binary. As soon as you do that, you're already a serializable, and the compiler does that automatically. Yeah. So in this ping pong example, we spawn two local actors, one for pong and one for ping. The way you do it, instead of having a module function name, you just have a monadic value, a process value, and it has all the steps you need in the actor. So, and in this particular example, they're using the get self PID, which is the self on Erlang. They're using the expect API, and yeah, they're doing ping pong there. And one question I have for you guys. What do you think is going to happen if I send to the ping or pong actor a message that doesn't match the pong or ping type?
Will your type system even allow it?
Yeah, because you expect remembers set serializable values. And ping and pong here, we implemented a serializable, so you can cast that. Like, there's a way to do casting like that in Haskell. It's kind of like dark magic, but once you learn, it's pretty cool. And what do you think is going to happen? Like, any question, like any suggestions? No idea? I have no freaking clue.
Deadlock?
No. Basically, it's going to ignore it. It's just going to send it to the dead letter. Well, there's no such thing as a dead letter actor on the system, but it's just basically going to have it on the queue up until some until a point where you do a spec with that specific type. Until you don't do that, the message is going to be on the queue there. So you have to be really careful when you're specing stuff, and be sure to do a match any type of messages, because if you don't do that and for some reason some other actor is sending messages that you're not expecting to your actor, it's going to start accumulating memory and it's going to crash eventually. So this is the kind of things the problems you arrive to when you're not using the OTP-like libraries. So don't do that. So in this receive example, here we use the receive timeout, which will be the equivalent to the receive and after. And the receive timeout here uses microseconds as the delay. In Erlang, it's milliseconds. And then we start doing matches for all the different kinds of type messages we can receive. So we have a match for when we receive a respond message. We have a match when we receive a process monitor notification. And if the timeout passes and you didn't receive anything, you're going to get a nothing value. Yes.
Explain the backslash.
The backslash is a lambda. So this way you're creating an anonymous function that receives a response or a process monitor notification value, and then you have the body after the arrow. And this function particularly returns a type called maybe, which represents something that can fail or not. And in the case of timeout, timeout can fail, and you cannot receive anything on a timeout. And if that's the case, you do something on the nothing branch, and in case you receive the answer, you have the answer of the just value. This will be the equivalent code in Erlang. You can see that Haskell is more verbosy because you have types, and you have to match on the types. So, yeah. One more Haskell-ish approach, though, is using channels, where when you create a channel, you receive two records. One that is the send port of the channel, and one that is the receive port of the channel. And when you create this channel, it's bounded to one type only, and whatever you receive there is going to be always of the same type. And that way you can ensure that you're not going to receive like crazy messages that you're not expecting. Of course, that's the only way you're receiving your messages. In this particular example, we are creating the ping, the channel that does send ping and sends a pong reply. And we create an actor pong that receives the send ping, so where the pong can communicate to the ping actor through that, as we do it here. And the pong creates also another two channels so that the ping actor can communicate to them. This example is a bit cumbersome, and whenever you want to use this specific pattern is when you want a stream of events from an actor, and you want to have it as a channel, basically. One nice thing of the API is that when you're creating these two ports, the sending port is serializable, so you can send it to other actors, and many actors can communicate to one specific actor through that. But the receiving port is not. So, and that's because the receiving port is not serializable. It doesn't implement the interface. So you can, on your API, you can restrict what you can send and what you cannot send through different actors by using the type system. And that's pretty nice because, for example, they made the really conscious decision of not being able to send any mutable variable through this messages, because it doesn't make sense. You don't want a mutable variable that accesses memory from one machine to the other. That doesn't make sense, so it's not serializable. So that's a nice way to keep things in order. Even though you have a shared memory model, you don't actually send those variables to different actors. That's pretty nice. And when you want to monitor, it's the same API as Erlang. You have a monitor where it receives the process ID and return a monitor wrap, and you can do comparisons with it, like in this example, where we are having this contrived example of a pong without a ping, and it eventually is going to time out and it's going to die, and the actor that spawned the pong is going to receive the process monitor notification. Like if I have it here, this actor is monitoring the pong PID, and then it's doing a match with this function, handle monitor error, and receives the monitor wrap as a parameter. In this particular example, I'm using one of the nice features of Haskell that is partial application. Like whenever you implement a function in Haskell, all the parameters are purified. So when you pass the first parameter to a function, you return a new function that expects the second parameter or the third parameter up until the result. And you can partially apply the function and pass it over. And this is exactly what I'm doing here. I'm having a function that receives both a rep and a notification of a process. And I'm calling here on the top the handle monitor error, passing the value that I have right now, which is the rep. And this API is going to see this as a function that just receives a process monitor notification, even though I partially applied before. That's pretty nice. Yeah. And linking actors is basically the same thing. You have a way to specify a process ID, and as soon as you do that, whenever that actor dies, you're going to die. It's a one-way relationship, and also it's idempotent. So if you link to the same actor many times, nothing's like it's gonna do it just once. And if you want to, like, you have also the opposite that is on linking, which I forgot to put in the slide, but yeah. In this particular example, it's the same as before, but I'm just linking to the process. In case any of these two fails, for some reason, the other one's gonna die. Yeah. Okay, so this is the interesting bit of Haskell complications on this model. In order to serialize functions in Haskell, they create this abstraction of a closure, where you have to use this make static closure function and specify the name of the function in order to send it over the wire. This is always required whenever you want to send functions to other nodes. And this notation over here, the dollar, it's template Haskell. How many people have used Haskell here before? Okay, so template Haskell is a way to generate Haskell code on the fly, on compilation time. So when I'm doing this $make static closure, make static closure is a macro that navigates the abstract syntax tree of Haskell and create other things. And this is like a facility for sending stuff. Like it creates a lot of boilerplate code on the background in order to send a function. And in order to send a function, we need to serialize it to a closure. The closure must be defined in the process monitor, of course, otherwise it's not going to work. The only closures that are serializable are the ones that are on the process monitor. I cannot serialize an I/O closure. And in order to use this function over here, remote actor, I need to call remotable on it before. So the way it works is that you have this concept of a table that maps symbols to functions. And when I'm doing the remotable, I'm saying this function, please add this function to this table. And later on, I have to use that table and pass it on the node creation. I go back to the node creation pretty quickly.
You just want to pass it?
I pass it, yeah. Here, there. Do you see that? Secondly, node init remote table. Like, I need to, every time I do a remotable, it creates a record that I can pass to this function, and it will add it to the remote table list. And that's the way how Cloud Haskell knows, oh, I know who you're talking about, so I'm just going to call a function. And that's the specific reason why you need the same binary in all the nodes. I'm going to show an example of remotable in just a sec. So in this particular example, I'm doing an add operation that can be remotable. And it's going to be the same as a vanilla process action. It's just that there's some limitations on the closure implementation. The first one is you lose the niceties of Haskell of having partial application of parameters. So you need to pass all the values at once, and that's why you have a tuple of 3 values here as a parameter instead of just 3 arrows. If you don't do it that way, it's not going to work. And in this particular example, we're receiving the PID of whoever wants my sum of my operation, my result, and the 2 integers. And I send it back. And in order to make it remotable, I do that bit down there on number 3. So as I said before, this remotable creates this record, this function called remote table. And when you have this remote table, you're gonna pass it to the init remote table, and it's gonna add all these functions one by one. So I have to move a little bit further. Limitations, boilerplate, a lot of boilerplate in order to achieve the sharing of a function between nodes. It's not Haskell, it kind of sucks, seriously. And yeah, like the limitation I have been talking, like what bugs me. And some concurrent problems we have here, like the problem we were having before with actors that can have race conditions and like the API being complex by using just the raw constructs. You use what is called a distributed process platform library, which has all the abstractions of OTP, so that you don't shoot yourself in the foot. And I'm gonna go pretty quickly through them because I don't have enough time. So it's basically the same API, it's a ripoff of Erlang's OTP. You have cast and call. You have a way to manage the state on the actor, the same way you will have with state machines on the managed process, on the server process, gen server, sorry. And allows formal instantiation and shutdown. So this is how it would look in Haskell. You have your functions, which could be cast handlers or it could be call handlers, and then you have this process definition that ties everything together, where you specify the API handlers and you pass the functions that you're creating, all the different handlers you're creating. In order to send stuff to the actor, you need to have like types specific for the kinds of messages you want. Otherwise, like it's a bad way to do it if you don't do it that way. I have to move fast. And this is the API where you can specify shutdown handlers, when you receive a timeout, when you have exit signals, when you receive messages that are not on the cast call protocol, then handle message policy where you have a dead letter actor or you have a drop it on the line. You have like many different options you can choose from, the same way you do with Jet Server. And this is an example of how you initialize an actor where you can specify if the initialization was okay, as we do up there. And you can specify if there's going to be a timeout after initialization, like after this amount of time if I don't receive a message, I'm going to have a timeout. And this specific example is just an infinity. Ways to implement, like you can do several things on each of the handlers. You can stop the actor, you can continue the actor, you can do a timeout when you receive messages. You can do the same thing on call, like but call you have to reply a result, otherwise it's going to fail. And this is the interesting bit. This is normally how you would do it in Erlang. You have like cast to one specific gen server, you receive the process ID, and then you start sending cast to it. Well, it's not the way you do it in Erlang. In Erlang, you will do this. You'll wrap cast, call, all those guys on specific functions. But Haskell goes to the next level, and it allows you to wrap the process ID into a new type. So you can create a new identity for your process ID and make the API that works for those specific kinds of actors specific to that process ID. So if you try to use this function, add or get some with a process ID that wasn't created through the API you provide, it's not going to compile. So that's a really nice add-on that you can have thanks to types. So yeah, this is how you use it. In this case, will cause some compilation error. Yeah, there's a lot of things to, like the same benefits you have with Jet Server, basically. Actor supervision, you know why supervisors are used. This is the record, like the same way you have a managed process record, you have a record for specifying things. And you can specify all these different things. Sorry, I have to run. You can change shell specs this way by specifying the Clojure down there, and start the supervisor like that, and have like different ways, like even add them dynamically to the supervision tree, the same way you do with supervisors in OTP. And those remarks. We are not quite there. We're not quite there yet. There's a lot of things to work. But it's nice to, like, it has a lot of potential though, and there's a lot of power in Haskell. And as soon as they fix the software, I think there's SOC. I think it's going to be a really good thing to be considering for using. Yeah. This is our resources. I'm going to publish this slides soonish, and thank you. questions? Yes?
Use Haskell, does it make the job of actually proving it correct easier? I know you don't have to worry about the side effects, but as soon as you start getting into things like state machines, theoretically provable abstractions, then you're looking less at the human error and more at
Like most of the times you're going to do those kinds of validations once you receive the messages. Like the interactions, the idle part of a process model is not going to get too much benefits out of the quick check way of doing things.
I don't mean that. No, I mean like when you've actually implemented something where you've got your peer-to-peer client server, whatever, you've got a protocol, you've got the process on either side that are handling it. How do you prove that that action is correct, that it's not going to fall into a state where you don't have an answer? In other words, it doesn't bring error statements, can't handle it.
Basically, the only way to fix a concurrency problem in Haskell is just seeing the traces on the messages and how their state react to those messages and test that. Haskell is really good to ensure that whenever you're doing refactoring, whenever you're changing code, or whenever you want to do validations on the mathematical nature, you have the tools to do so and prove them. But when it comes to concurrency, all bets are off. It doesn't matter if you're using Haskell, if you're using Erlang, or if you're using Go or JavaScript. I don't know what Kool-Aid they're going to invent next. But concurrency is hard. There's no escaping from that. And the best way I alleviate concurrency issues are basically using events and reducing state with those events and log that and see how my state react to different events. And in case I get to a state that is not the one I'm expecting, I see the logs and see which events I'm receiving which time and store those things and replicate that through a test, like being able to send that myself on a control test and see why.
Record replay.
Record replay, exactly. Any other questions? Yes?
Do you know about production deployments? Where this is running?
No, not really. I know some people on Birdseye are using it, but I don't know where. They started this project, and I don't know if they're still actively working on it, but they're using it for sure.
There's a few Belgian companies using it as well. I think French or somewhere around there.
I think INDC, locally here, I think INDC was looking around. We were using it for our own stuff, and it has it wasn't an easy decision to make because we could either implement something that was less, say, ambitious than this, and not get all the niceties they already have, or just load all that library in our minds and work from there. And the decision I think was the best given the circumstances, but it's really edgy. There's a lot of things to consider. You cannot even install it on the standard way you will do it with Haskell applications. You have to actually use a sandbox, which is you download the thing from GitHub and add it to your your development environment, and it's not ready. It's not ready yet. Shameless plug before leaving here. I'm gonna do a Haskell workshop for the Polyglot meetup. In case you're interested in getting more details about Haskell, not this thing particularly, but Haskell in general and all the benefits that Haskell provides, feel free to sign in for the workshop.
When is that?
Next Friday. Yeah.
So meetup.com.
That's on the Polyglot page.
Is that an evening?
It's going to be a 7-hour workshop, so it's whole day.